last problem, don't be fazed by this question, and let's look at a phase diagram of gold and SN, AUSN. So we could see several intermetallics, and so let's go ahead and answer this question. So even though the question, whatever it's going to say, I want to be able to kind of draw out or write basically what are the different phases in this problem. So I'm going to zoom in a little bit here just to give us some better context. So I have these intermetallic compounds here. So this is my pure alpha phase. So what is this liquid here? So what is this region here? This is going to be liquid plus alpha. What about this region? I'm touching on this side beta. This is liquid, so this is going to be beta plus liquid. What about this side right here? Well, this is going to be gamma plus liquid. What about this side? This is going to be delta plus liquid. What about this side? It's also going to be delta plus liquid. And what about this side here? It's going to be eta plus liquid. What about this side over here? It's going to be, or this is, this is zeta. This is eta plus liquid. And what about right here? Let's go back over here now. This is going to be alpha plus beta. This is going to be beta plus gamma. This is going to be gamma plus delta. And this is going to be delta plus zeta. And this is going to be, right here, this two-phase region is going to be zeta plus eta. There we go. First question, done. So we filled out all sections of the phase diagram. Let's also kind of write out, because I know I'm going to do invariant points. So this is going to be congruent. This is going to be eutectic. What is eutectic? Liquid to alpha plus beta. I am going to do this symbol. I'm going to do this symbol. So this is going to be my square. I'm going to do my kind of star for pereutectic, which is going to be liquid plus alpha goes to beta. For my eutectoid, I'm going to do my diamond like this. So eutectoid, that's going to be essentially a gamma to an alpha plus beta. So single pure phase of solid. And then for this one, I'm going to do just a triangle pereutectoid. Which is going to be a two-phase solid region, so an alpha plus a gamma to a beta region. There we go. Those are all types of our invariant points. So I see a congruent melting point right here. I also see another congruent melting point right here. And I also see one more congruent melting point right here. So those are all my congruent melting points. What else do I've got here? So where's my eutectic? So eutectic, here's eutectic here. Here's a eutectic right here. Those are all my eutectics. What about my pereutectics? So what's the symbol there? That's a star. So I see a pereutectic right here. I see a pereutectic right here. And let's see, any other pereutectics? Searching. Yes, pereutectic right here. So do we have any other types of invariant points here? So remember, when you're looking for this type eutectics, we're looking at our bunny ears, right? So we look at this, and this. For our peris, we're looking at something like this. So something like that's this, or something that has a little bit of a width to it as well. So that's kind of the key idea here. So let's see what else is going on here. But yeah, that's essentially what we've got. Those are all our invariant points that we can that we're working with here. So yeah, that is all we've got. So now let's go ahead and hopefully that was part of the question. So those are all my invariant points. Great. All right, I've indicated all my congruent melting points. I've done my invariant points, and I've been sure to label, and you can kind of label each of the invariant points, but we've already labeled them there. So that's all we've got here for in terms of our invariant points. So now let's answer the last part of the question. So what is the degrees of freedom at 50 weight percent and 325 degrees C? So Professor Steinel should have indicated weight percent atomic U. So this is 30, so 35. So it's about right here. What was our temperature? I'm going to kind of erase right here right now. Do drawing, erase. Let's go ahead. So I think I was at 35, which is right here. So 20, 30, 35. And let's go down. So 35, or actually, excuse me, 50 weight percent, 325 degrees C. So that'll be easier. So 50 weight percent, and we were at 325. So 300, So 325, 350 is right here. So we have something, let's say my composition is right here. So in this region, what am I? I am liquid plus delta. So in this region, I'm using my degrees of freedom, D plus P equals C plus 1. So equals, let me just erase that. D plus P equals C plus 1. So my number of components is 2. My components are gold and SN. What are my number of phases in here? This is equal to 2 here. So now my degrees of freedom is 1. So that's my degrees of freedom in here because, again, I instantaneously will phase separate into liquid of this composition and then a solid in this composition. So if I change temperature, my composition is fixed. If I change composition along this line or this line, then my temperature is fixed. So that's my degrees of freedom is equal to 1. Great. Now we're asked what's the composition in each phase, and then what is the fraction of material in each phase. So let's go ahead and answer that question as well. So I know, for example, my composition in the liquid phase is going to be right here. So I'm going to say that this is like, so my composition in the liquid is going to be like 42%. My composition in the solid, the delta, so my composition in the delta phase is going to be equal to about right here, say 62 as well. And I know that I'm in a two-phase equilibrium means that what? My chemical potential of liquid is equal to chemical potential of my solid. That might pop up on your exam. Be ready for that one. Be sure to kind of be able to kind of identify those kind of key relationships. Chemical potentials are equal, and thus I'm in two-phase equilibrium. That might show up on your exam. So anyways, so now I could figure out what's the fraction of my liquid. So fraction of my liquid is going to be my concentration of the solid minus my C naught. C naught here is given in the problem statement, 50 weight percent. So 50% divided by my, basically the C delta minus concentration of the liquid. And then my fraction of the solid, or my delta here, is going to be concentration naught here minus concentration of my liquid divided by C naught minus Cl. So we can see at this 50 weight percent, we're kind of closer to the liquid. So when we kind of calculate that out, it's going to be that kind of same value. So again, you want to actually calculate out the value. So again, it's going to be, so we have basically for here, this is going to be equal to 62 minus, so it's going to be 12 divided by 20. And this is going to be over here, C naught is 50 minus 42, it's going to be 8 divided by 20. So we can see that we're closer a little bit to here. So this is going to be, should be a little bit higher, but this is going to be, we're going to be closer to liquid. So our fraction of liquid will be larger, and that's reflected in our kind of calculation here. So that is it. So don't be kind of thrown off by your phase diagrams. One last question. Which has a higher diffusivity? Eta, or basically a gold or SN? So if I'm interdiffusing, so how much gold can I fit into SN? Not much, but how much here, how much of SN can I fit into gold? Much, much more. So diffusivity of SN greater than diffusivity of gold, based on just this solubility. So maximum solubility appears to be higher of SN into AU. So larger diffusivity, possibly. All right, that is it. So study well, get a good night's sleep, eat, and be ready, and you're going to do great on this exam. So remember, show your knowledge at all points, and I'll see you during the exam day. Thanks.